So let's just talk about the Floyd Warshall algorithm. So here we can find the shortest path between every pair of the vertices in a graph. So in case of Dijkstra algorithm, from one single source we can find the shortest path to all of the vertices. But in case of this Floyd Warshall algorithm, here we find the shortest path between every pair of the vertices in the graph. That means from the vertex 1 to 2, 1 to 3 and 1 to 4 we find the shortest path. Here 1 is the source and all of these are the destination. Similarly, we can start from the vertex 2 and we can find the shortest path from 2 to 1, 2 to 3 and 2 to 4. Similarly, 3 can be the source. We can find from 3 to 1, 3 to 2 and 3 to 4. Also 4 can be the source. From 4 we can find 4 to 1, 4 to 2 and 4 to 3. Now here we can use the Dijkstra algorithm 4 times to find the shortest path from all of these single source. Or we can use the Floyd Warshall algorithm, which is based on the dynamic programming, and unlike the Dijkstra algorithm it can handle negative weight edges. So let's just see how we can find this all pair shortest path. So here we're gonna use one 2D matrix to represent the cost between all of these vertices. So because in the graph we have 4 vertices, so that means our matrix will be 4 by 4 matrix. Now here inside the matrix, because from 1 to 1 this is the same vertex, so here cost will be 0. So that means all the diagonal cost will be 0. Now from 1 to 2 we have the cost 2. So from 1 to 3 there is no direct connection, so it will be infinite. From 1 to 4 we have the cost 3. Similarly from 2 to 1, you can see from 2 to 1 there is no direct connection. Because there is no direct connection, so it will have the cost as infinite. Now from 2 to 3 there is the cost 7. From 2 to 4 there is no direct connection, so it will be infinite. So similarly we're gonna fill all of this data. So we are done with the D0. Now we're gonna compute the matrix D1 and we're gonna derive this matrix D1 from this matrix D0. So here we're gonna use the dynamic programming approach to find the best route between two vertices. So suppose we have some cost from 1 to 2. Now we do not know if that is the best route or not. So in that case, we're gonna compare this particular route with some alternate routes. So we're gonna take some alternate route through the vertex 3 and we're gonna compare if that is smaller than this direct route or not. And also we're gonna take another route through the vertex 4. So among these routes we're gonna take the best or the smallest one. So this way we can dynamically compare these routes and we can find the best or the shortest path between all of the pairs. So here in this case, so we're gonna derive this D1 from this D0. So in this D1 we are using the vertex 1 as the intermediate. So that means its values will stay as it is. So the vertex 1 row and column values will stay as it is. So suppose you are going from 2 to 3. So if we are going from 2 to 3, so the direct cost from 2 to 3 is 7. Now we're gonna go through the vertex 1 and we're gonna check if that is better than this direct path or not. So we're gonna use this vertex 1 as the intermediate and we're gonna see if we found some better path or not. So here in this case from 2 to 3 we have direct path as 7. So this is 7. Now if we go through 1, so if we go from 2 to 1, you can see there is no direct connection, so this is infinite. And 1 to 3 and 1 to 3 there is also no direct path. So both of them are infinite. So because 7 is better than infinite, so that means we're gonna keep the 7. So again from 2 to 4, so from 2 to 4 you can see we had the distance as infinite. Now we're gonna take the route via the vertex 1. So from 2 to 1 there is no direct connection. From 2 to 4 there is no direct connection. So that means we're going to have the infinite. So we're going to repeat the same process. Now we're going to compute the matrix D2, and the D2 will be derived from this matrix D1. Now here in case of D2 we're going to use the vertex 2 as the intermediate. So that means this second row and the second column will stay as it is, and we're going to recompute all of these other distances. So the diagonal element will stay as it is. So now from 1 to 3, so from 1 to the vertex 3 we have the cost as infinite. Now we're gonna take this vertex 2 as the intermediate, and we're gonna check if we found some better path or not. So from 1 to 2 we have the cost as 2, from 2 to 3 we have the cost as 7. So because 7 plus 2 is 9, so 9 is better than infinite, so that means here we're gonna take 9. Now from 1 to 4, so from 1 to 4 we have the cost as 3. Now we're gonna take the vertex 2 as the intermediate, so from 1 to 2 we have the cost 2, from 2 to 4 there is no direct edge, so it will be infinite. So because 3 is better than infinite, so here we're gonna take 3. So this way we're gonna fill all of these positions by taking 2 as the intermediary. So we're done with the matrix D2. Now from the D2 we're gonna derive or compute the matrix D3. So here we're gonna use the vertex 3 as the intermediate vertex. So that means here the third row and the third column will stay as it is, and we're gonna recompute all of the other values. So now first of all from 1 to 2. So from 1 to 2 we have the direct cost as 2. Now we're gonna take the vertex 3 as the intermediate, and we're gonna check if we found some better path or not. So from 1 to 3 there is infinite. From 3 to 2 also this is infinite because there is no direct path. So because here 2 is better than infinite, so we're gonna take this 2. So this way we have to compute all of these values. Now here from 2 to 4, so from 2 to 4 you can see we have this infinite when we took this direct path. But now if we take this vertex 3 as the intermediary, so in this case from 2 to 3 we have the cost 7, from 3 to 4 we have the cost 5. So 7 plus 5, 12 is better than infinite, so that means here we're gonna have this 12. So this way we're gonna fill all of these values. So we're done with the D3. Now we have to compute the D4, and we're gonna derive that from the D3. So here we're gonna take this vertex 4 as the intermediate vertex, that means the fourth row, and this fourth column will stay as it is, and we have to recompute all of the other values. So here from 1 to 2, so the vertex 1 to 2 we have the direct cost as 2. Now we're gonna take this vertex 4 as the intermediary. So from 1 to 4 the cost is 3, from 4 to 2 we have minus 2. So you can see 3 minus 2, so 1 is better than 2. So that means here we're gonna have this update, so new value will be 1. So next from 1 to 3, so from 1 to 3 we have the cost as 9, so that is the direct cost. Now we're gonna take this vertex 4 as the intermediate vertex. So from 1 to 4 we have the cost as 3, from 4 to 3, from 4 to 3 we have the cost as 4. So here 7 is better than 9, so that means here we're gonna have 7. So this way we have to fill all of the other positions. So we are done with the D4. So this D4 matrix is the all pair shortest path matrix. So from this matrix we can find the shortest path between all of the different pairs. So here is our formula. So suppose we are computing position of a matrix I, J. So in that case, dk is our matrix, that is the current matrix. So to compute that, we have to look into our previous matrix. So that means we're gonna find the minimum in our previous matrix, which is k minus 1. So because that is d1, that means we have to look into d0. Similarly, to compute d2, we have to look into our previous matrix d1. So here the previous matrix is dk minus 1. So here we're gonna look into the position I and j. So that means that is the direct distance. So we're gonna compare this with the distance through one intermediary. So that means from I to k, k is this intermediate vertex, plus d of k, j. So here basically comparing the direct cost with the cost through this intermediate vertex, and we're going to take the minimum of them, and that will be our new cost because that is the efficient one. So this way, to compute d1, we have to take the data from d0. To compute the d2, we have to take the data from d1. So this process will continue to go on, and at last we're going to have this matrix which will contain the shortest path between all of the pair of vertex, and this is our formula that we are using. Now here the Floyd Warshall algorithm will be used when the graph is dense, and also the graph has this negative edge. Otherwise, if the graph is sparse and there is no negative edge, in that case we can use the Dijkstra algorithm multiple times. So that's about this Warshall algorithm. So hope you understand. Thank you.